Good evening, everyone. This is Ahmed Hamdi, the course instructor, and it gives me pleasure to be with you tonight discussing the October 2020 optics exam. This lecture was given online, but due to some technical problems with Zoom platform, this resulted in that the lecture wasn't recorded. So I am going to discuss the lecture again in offline mode and give you the explanations and answers that was already given. So here we start with the first question, and these are the game rules for the online course, and I will hope that you will be able to join online in the next sessions. And starting with the first question, regarding spectacle correction of aphakia, which one of the following statements is most likely to be true? A ring scotoma is due to prismatic effect of the aphakic lenses, or it produces barrel distortion, or objects appear further away than they really are, or the relative spectacle magnification is 2.5. So what will be your right answer? Yes, so the right answer is a ring scotoma occurs due to prismatic effect of the aphakic lenses. The prismatic effect can produce many problems. One of them is the ring scotoma. The barrel distortion is caused by the prismatic effect of high myopic lenses or minus lenses. Objects appear closer than they really are with the aphakic lenses, and the relative spectacle magnification is 1.3 only. So the explanation that we said before in the lectures is that those who have aphakia and look through the periphery of the lens, when there is an object appear at the periphery, it will undergo prismatic deviation. It will undergo, due to the prismatic effect of the lens periphery, the object images or the rays will deviate toward the base, causing the object or the image to appear more displaced toward the apex. So when the patient moves his eyes to look at it, the light rays coming from it will undergo more deviation, causing it to disappear. This is called the jack-in-the-box phenomenon, since the object started to appear and disappear. The optical problems with spectacle correction, one of them is the magnification, as the relative spectacle magnification is 1.3. This is one of the problematic effects of the spectacles, but sometimes it can show advantage in the patient with the patient looking at near target or looking at targets, because they appear more large, so that they appear closer than they really are, as if the patient is looking through a magnifying loupe or looking through a magnifying lens. It will produce a smaller image than the object, but since that it is closer to the eye, it will stimulate larger number of photoreceptors, causing more larger image. A second effect by the prismatic effect of the lens of the aphakia is that it can cause image distortion. This image distortion can be in the form of a pincushion effect here, while that of the high myopic lenses can cause distortion of the barrel shape. So this is that of myopia, and this is that of the hypermetropia. Okay, let's move to the next question regarding axial myopia. Which one of the following statements is most likely to be true? It increases with age, or it is secondary change in keratoconus, or it's corrected by concave lens, or the second principal focus is behind the retina. So take a few seconds to think. Yes, I think that you all got it right. So it increases with the age, but up to limit. So it doesn't increase for lifelong, but to a certain age. And it is secondary change to keratoconus. This is wrong. It will be the refractive myopia will be the secondary change in keratoconus. It is corrected by concave lens. Yes, this is true. And the second principal focus is behind the retina in case of hypermetropia, not in myopia. So myopia, as we mentioned before, can be classified as axial myopia or refractive myopia. Axial myopia due to increase the axial length, while refractive myopia can be either curvature myopia as in keratoconus due to increased curvature of ocular media, or index myopia as an increase in refractive index as with nuclear sclerosis. The axial myopia can be classified into different types, but all of them can stop at certain year. For example, the simple myopia will stop at 25-year-old, while the degenerative myopia will stop at 35-year-old. For myopia, the F2, when it is the F2 is on the retina, then the punctum remotum will be in front of the eye. This is in contrary to hypermetropia, where the F2, when the F2 is on the retina, the punctum remotum will be behind the eye. The third question is about the electromagnetic spectrum. Which one of the following statements is most likely to be true? Blue-green is longer wavelength part of the visible spectrum, or light in the infrared spectrum is blocked by the cornea and sclera. The 315 to 400 nanometer part of the spectrum is absorbed by the crystalline lens, or the visible range is between 500 nanometer and 760 nanometer. So the correct answer is C. So why other options are wrong? The blue-green spectrum of blue-green waves are the shorter spectrum of the visible spectrum, or blue-green are shorter wavelength in contrary to red. And light is in the infrared spectrum is not blocked by sclera and cornea, as they are absorbed by the cornea, causing it to reach the lens and to reach the retina, causing a famous problem called solar retinopathy. So why we are advised to avoid looking to the sun during eclipse, to avoid exposure to infrared rays which can penetrate through the cornea and ocular media, leading to reaching the retina, causing a foveal burn. The 350 to 400 nanometer part of the spectrum is absorbed by the crystalline lens. This is true, and this is the range of ultraviolet A radiation. The visible range between 500 and 760 nanometer, this is wrong, and because 500 is within the green-blue range, but this is not correct. So as we mentioned before, that the visible spectrum is ranging from the blue light, which have a wavelength of 380, to the red light, which have wavelength of 750. So this is called the visible spectrum. As we move from the red to the blue, there will be decreasing wavelength and increasing energy and frequency. This is very important. There are different absorbing characters or blocking characters of the ocular tissue to different waves of the visible and invisible spectrum. For example, the ultraviolet rays C and B of the infrared rays are absorbed by the cornea and sclera. As the ultraviolet rays, when absorbed by the cornea, it can cause this famous famous clinical picture of photophthalmic keratitis. The lens can absorb the ultraviolet A rays, which can be attributed sometimes to be one of the responsible mechanisms for cataract formation. And finally, the retina absorbs the ultraviolet A, or the ultraviolet A can reach in some amounts to the retina, and all the range of infrared rays can pass through different ocular media to reach the retina, which can cause this solar maculopathy or solar retinopathy. You can see that the visible spectrum can pass through the ocular media to reach the retina. The ultraviolet A can pass through the cornea and lens. It's mostly blocked by the lens, or it is absorbed by the lens. Some very minimal amount reach the retina, while the ultraviolet B is blocked by the cornea. So this is the ultraviolet B, which is responsible for the photophthalmic keratitis. Ultraviolet A can cause a bluish discoloration of the images when after cataract extraction and IOL implantation, if the IOL doesn't have UV filter, because the protective effect of the lens against the ultraviolet A is no longer present. So this is from Elkington, can show the different range of wavelength of different waves. So you can see that the ultraviolet A has a range of 315 to 400 nanometer, and the cornea and sclera absorb the ultraviolet C and the ultraviolet B, infrared B and infrared C. The crystalline lens absorb the ultraviolet A and the visible light or the infrared between 400 to 1400 nanometer pass through the ocular media to fall on the retina, which can sometimes call thermal retinal damage. Let's move to the next question about polarization of light. Which one of the following statements is most likely to be true? A polarizing substance makes all incident light vibrate in the same plane, or it occurs when the light passes through a narrow opening, or light may be polarized on reflection from a plane surface. When polarized, light has increased radial intensity. So what will be your answer? Exactly. So let's analyze the answer. A polarizing substance makes all incident light vibrate in the same plane. This is wrong. So what is the function of the polarizing substance is to allow transmission of the light in a certain plane or of the same plane, but it doesn't convert the wavelengths or the other or the light waves of opposite or of different planes to the same plane. In other words, the effect of the polarization doesn't convert the light rays, but it just allows the transmission. This is the function of the polarizing substance. It causes, the diffraction is what happens when the light passes through the narrow opening, and light may be polarized on reflection from a plane surface like the surface of water. This is right. And when polarized, the light loses some of its energy, or loses some of its radiant intensity. So according to Elkington again, the ordinary light waves vibrate in more than one plane. This is what's called the unpolarized light. The electromagnetic waves vibrate in different meridians, like vertical, like horizontal, and when they pass through a polarizing filter, this polarizing filter allows only transmission of certain plane of waves, but it blocks the transmission of the other planes of wave. But it doesn't convert the horizontal to vertical, it just allows vertical to pass. So how can polarized light be formed? This can be done by intersecting with a polarizing substance like calcite crystals. And in this case, as we said, the polarizing medium will reduce the radial intensity but doesn't affect the spectral composition or doesn't affect the color components of the light. The second method for producing a polarized light is through the reflection from a plane surface. When there is unpolarized light where the light waves are vibrating in all planes and it will hit the plane surface, as we mentioned before, some will reflect and some will refract. But if the angle of incidence will be equal to the angle of will be equal to the polarizing angle of this substance, which is dependent on the refractive index, this will result in that the part of the light will be reflected as a polarized light. So polarized light can be produced by reflection from the surface of a plane surface. Regarding the image by concave mirror, which one of the following statements is most likely to be true? Catoptric image 3 is an example of this image, or it is always diminished in size, or it is the same type of image whatever the object distance, or it may be real or virtual image. So the right answer, it may be real or virtual image. So catoptric image 3 is an example of image produced by the convex mirror. As image formed by the concave mirror can be of the same size or diminished or increased in size. This will be dependent on the location of the object. So it is not the same type of image, whether the object, whatever the object distance, but the distance can make the image either real or virtual. As you can see here, it may be real or virtual. This is the right answer. Let's review the characters of the Purkinje-Sanson images. We said before that we have 4 Purkinje-Sanson images according to a reflection from different ocular media. So the anterior corneal surface will produce the first Purkinje-Sanson image. The posterior corneal surface will produce the second Purkinje Sanson image. The anterior lens surface can produce the third Purkinje Sanson image, and finally, the fourth or the posterior corneal lenticular surface will produce the fourth Purkinje Sanson image. The third image here is produced by the convex surface or the convex anterior lens surface, and so it is not produced by concave mirror effect. As you can see here, a practical example for concave mirror, like the use of it in headlights or as a magnifier, so the image is not always diminished in size. The character of the image will be dependent on the characters of the object. So this, in other words, if the object is present between the center of curvature and the focus, then the image will be present beyond the center of curvature, and it is virtual and it is real, enlarged, and inverted. If the object is present at the center of curvature, the image will also be present at the center of curvature, and it will be real, inverted, and of the same size. If the object is present at the infinity, then its object or its image will present at the focus. While also if the object is present at the focus, then the image will be present at the infinity, or there is no image is formed. If the object is present beyond the center of curvature, then the image is formed between the center of curvature and the focus, and it will be diminished, real, and inverted in size. The next question, it is about the dispersion of light, so which is true. Dispersion from red to blue in the human eye is approximately 2 diopters, or it causes the prismatic effect at the periphery of high-powered lenses or longer wavelengths. Longer wavelength light is deviated more than the shorter wavelength light, or the dispersive power of a material is related to the refractive index. Yes, the first one will be the correct answer. So the dispersion of light is a character in which there is a breaking down of the wavelight to the color components, and this occurs at the human eye due to prismatic effect of the ocular media like the lens and the cornea. So both they will be dispersed between the blue and red color, and this dispersion will be over a space or over a distance of 2 diopters. It causes the prismatic effect of the periphery of high-powered lens. Although this sentence looks normal or looks right, but actually this is not the result of dispersion, but it is the reverse, meaning that it is the cause and the dispersion is the result. So the prismatic effect in the periphery of the high-power lens is what will cause the dispersion of light. The longer wavelength light is deviated more than the shorter wavelength. This is not true. The shorter wavelength, like the blue, is deviated more than the long or the red. The dispersive power of material is related to the refractive index. This is not true, and we mentioned it more than once during lectures. So dispersion is referring to the breakdown of the white light, like the sunlight, into constituent colors, like this. The more energy the light has, the more deviation, like the blue, and the less energy the light has, there will be less deviation. This character is present in the prism, causing chromatic dispersion, or this dispersive power of the prism is not related to the refractive index of the prism. You can see here, this is the lenses or the lens or the cornea, and it has a prismatic effect causing dispersion of light entering through the eye into the blue, from the blue to the red. So the blue will be deviated more because it has a shorter wavelength and higher energy, while the red will be deviated less because it has less energy and longer wavelength. And the range between the blue image to the red image will be in a range of 2 diopters. We mentioned before this experiment where the patient can wear cobalt blue glasses and the myopes will see the red better while the hypermetrope will see the blue better. This is again due to the chromatic dispersion between the blue and red. In the refraction of the human eye, it is subjected by chromatic aberrations, and the total dispersion from blue to red image is about 2 diopters, and the emmetropic eye will focus the yellow-green about 555 nanometer. You can see this is the emmetropic eye, showing the blue is focused in front of the retina, green in front of the retina, yellow at the retina, while the red is behind the retina. We use in the duochrome test the green and red instead of the red and blue because both of them straddle the yellow light by equal amount, about 0.4 diopters. Okay, let's move now to the next question. Regarding the prism, which one of the following statements is most likely to be true? A one prism diopter gives an apparent displacement of 1 centimeter to an object at 10 centimeters, or a base in prism is induced by nasal decentration of a concave lens. An object viewed through a prism appears deviated towards the base. To relieve the symptoms of exophoria, a base in prism is used. Exactly, to relieve the symptoms of exophoria, as a base in prism is used. So, a one prism diopter will give apparent displacement of 1 centimeter to an object of about 1 meter distance. This is one of the methods of notation of the prism. A base out prism is induced by nasal decentration of the concave lens, and we mentioned this in the lectures. An object viewed through the prism appears deviated toward the apex, not the base, and to relieve the symptoms of exophoria, like if you are using a relieving prism, we use a prism with the base against deviation. So if we have exophoria, we use a base in prism. Here we can see the notation of prisms. We have different methods like the prism diopters, like centroid, apical angle alpha, or angle of minimal deviation. The prism diopter, there will be apparent displacement of the image toward the apex by 1 centimeter when it is kept at 1 meter. So it is 1 meter, not 10 centimeters. And here we can see if we have a minus lens in front of the eye and we do nasal decentration toward the nose, then instead of the center of the lens will be in front of the center of the eye, actually it will be a prism in front of the left eye with the base out and the apex toward the nose. So it will produce a base out effect. The image formed by the prism has some characters. It will be virtual, erect, and displaced toward the apex, while the rays are displaced toward the base. As here you can see the object light rays pass toward the eye by undergo refraction of the prism. Then the eyes will show or will see the image of the object displaced toward the apex. There are different uses of the prisms. Some of them can be therapeutic. For example, if we are wanted to use exercising prism in which we are want to train the muscles or make the muscles stronger, as in case of medial recti in convergence insufficiency, so we use the base with deviation. But if we want to use a relieving prism, like for example, if a patient has diplopia and we want to relieve these symptoms of diplopia, so we use base against deviation. And this, like the example of that we had, the patient had exophoria and he has symptoms, so we use a base in prism as a base against deviation. Regarding the accommodation, which one of the following statements is most likely to be true? An emmetropic eye accommodates by 0.5 diopters to view at 2 meters, or the amplitude of accommodation is measured in centimeters. The stimulus is the apparent proximity of an object. Young myopes can accommodate to improve their vision. So the correct answer is that the emmetropic eye accommodates by 0.5 diopters to view at 2 meters. This is the first and the basic rule of the optics, which is the power of any lens will be equal the reciprocal of its focal length. So in order for an eye to see an object at 2 meters, it needs to accommodate about 0.5 diopters. The amplitude of accommodation is measured in diopters, not in centimeters, while the range of accommodation is what is measured in centimeters. The stimulus is not the apparent proximity of an object. So let's say, for example, if a patient is, if we put a minus lens in front of a patient's eye, he will accommodate in order to overcome this minus lens, and so we didn't approximate the object. So this is not the only stimulus. But the stimulus for accommodation is the blurring of the image. Young myopes can accommodate to improve their vision. No, young myopes, if they accommodate, the vision will worsen. So as we mentioned before, here is the relation between the power of accommodation and the focal length or the distance. So power equals 1 divided by focal length. In order to see an object at 25 centimeters, the eye should exert accommodation of 4 diopters. If the eye wants to see an object at about 50 centimeters, the eye should exert a power of around 2 diopters. If the eye wants to see an object at 1 meter, then the eye should exert about 1 diopter. And according to the question, if the eye wants to see an object at 2 meters, then it should exert accommodation of 0.5 diopters. The amplitude of accommodation is the difference in the dioptric power between the eye at rest or maximum accommodation. So let's say that the maximum accommodation of this eye is about 4 diopter, making it see object at 25 centimeters clearly. And this is an emmetropic eye, so the punctum remotum is at infinity, at which the accommodation is 0. Then the amplitude of accommodation will be the difference between the power of eye at rest and the power of eye at maximum accommodation, and it will be 4 minus 0, then it will be 4 diopters. While the range of accommodation is the distance between the punctum remotum and the infinity, which will be here the distance between the 25 centimeter and the infinity. Regarding the spherical lens, which one of the following statements is most likely to be true? For a contact lens, the first and second focal lengths are equal. Lens power is designated by the second focal length, or the nodal point lies between the first principal focus and principal plane. The second principal focus of a concave lens is posterior to the lens. Exactly. So for a contact lens, the first and second focal lengths are depending on the refractive media in front and behind lens, and in case of contact lens, they are different. The lens power is designated by the second focal length, as we just mentioned. This will be how can we determine the lens power. The nodal point lies between the first principal focus and the principal plane. No, this is not correct. The nodal point lies at the intersection between the principal plane and the principal axis. The second principal focus of a concave lens is posterior to the lens. No, it is the anterior to the lens. Let's see the explanation. So if we have a lens and there is medium in front, which is air, and the medium behind, which is air, then the anterior focal point will be equal to the anterior and posterior, or the first and second focal points will be equal. The issue comes when the refractive media are different, meaning that the light speed in the air is maximum, so it will make the focal length short. But when the light passes through the lens and come to another refractive medium like the glass, the light will slow down, making the focus more away. So the f1 will be shorter than the f2, resulting in that there are different focal lengths of the lens. And the practical example of this is the first and the second focal length of the cornea. So the cornea, in front of it like air, and behind it there is aqueous. So f1 will be 24.5, while the f2 will be 32.5. f1 is not equal to f2 because of the different media on both sides. You can see that here in the contact lens, it will be in front of the contact lens will be air, and behind the contact lens will be the cornea. So there will be different refractive indices in front and behind, result in different first and second focal lengths. The nodal point lies at the intersection of the principal axis and the principal plane, as you can see here. And the second principal focus of the concave lens is anterior to the lens. So here is the second principal focus of the concave lens. You can see that it is in front of the concave lens. And finally, the unit power of the lens is diopter, which is the reciprocal of the secondary focal length. And as you can see here, if we say that this lens has a power of 4 diopter, then the f2 will be 25 centimeters. If the lens has 10 diopters power, then the focal length will be only 10 centimeters. It is an inversely proportionate relationship between the focal length and the power. The next question, we have a patient wearing a +8 diopter spherical lens, and you are requested to decenter the lens horizontally in order to give the patient 10 prism diopters of prismatic effect. So how much would you decenter the lens? Question about lens decentration. Yes, it is 12.5 millimeters. So what is the rule that we follow here? It is the Prentice rule. Prentice rule mentioned that the prismatic deviation in prism diopters will be equal the lens power multiplied by decentration in centimeters. So by just following the equation, then 10 prism diopter will be equal 8 diopter multiplied by the decentration in centimeter. So the decentration will be equal 10 divided by 8 centimeters, and it will be equal 1.25 centimeters, which is equal 12.5 millimeters. The next question asking about the use of the spectacles and contact lens. Which one of the following statements is most likely true? Uncorrected myope will see better by moving the spectacle down to the nose. If moderate hypermetrope change from a spectacle to contact lens, the power will increase. Or to read, the presbyope can push their hypermetropic correction closer to eyes, or the back vertex distance is essential measurement for all myopes. Okay, B is the right answer. So let's review the answers. Undercorrected myope will see better by moving the spectacle toward his eyes, not on his nose, because by this way he will increase the effective magnification, or increase the magnification, or increase the effectiveness of the lens. A moderate hypermetrope will changes from a spectacle to contact lens power will increase. This is correct, because the hypermetrope, in order to gain a magnifying effect, like for example to read in a presbyopia, they will push the hypermetropic lenses down to their noses, because this will increase the effectiveness of the lens, or increase the magnification. And what happens when we do the reverse? Like what happens when we change from spectacles to contact lens, or moves toward the eye? This will result in decrease the effectiveness of the lens, or decrease the magnification. In order to compensate for this decrease in magnification, we need to increase the power. That makes the B is the right answer. Back vertex distance is not essential measurement for all myopes, but it is used for high myopia. Okay, this concept is very important for you to grasp and understand, because if you understand it well, you will do better for many questions in like this style. The myopia will push their glasses toward their eyes to gain a magnifying effect, and on the other hand, the hypermetropia, like the presbyopes, make the glasses down their noses in order to gain a magnifying effect. So why does this happen? Because we mentioned, according to the Knapp's rule, if the patient is wearing a spectacle at the f1, then the power of the lens will be equal to the emmetropic, or the image size produced by the lens will be the same like the emmetropic image size. However, this doesn't occur always, meaning that sometimes we are moving the lens away from the f1, or away from the eye, or more toward the eye. So what happens if we move the plus lens away from the eye? Like for example, if we are the plus lens, the patient is putting it on his nose, the back vertex increase and the image size increase. There is magnification, so that hypermetrope, when he is not comfortable with glasses, he make it down to his nose. And what happens if we change the spectacle to contact lens? The image size will decrease, the power will decrease, as we are now inside the f1 and we are moving inside the eye. So that we need to compensate for this by increasing the power. So the contact lens power should be more than the glasses power. The same goes with, or the reverse goes with the minus lens. As if we are away from the f1 or increasing the back vertex distance, this will result in to decrease the image size. But what happens if a myope push the glasses toward his toward his eyes, causing decrease the back vertex distance? This will cause that the image size will increase. So he will gain magnifying effect. And this is the explanation optically. So for hypermetropia, they have weak refractive system and the focus will be tend to be behind the eye. And what happens when we do plus lens is that the focus is moving further toward the eye, and it converges the light rays, making it more toward the eye from behind, and it moves forward. So as we put plus lenses, the image is moving forward, and also if we increase the power, the image will move forward, and if we move the lens itself forward, the image will move forward, making it in front of the retina, making it on the retina, making its effective power increasing, or the magnifying effect. That's why the hypermetropic patient tended to move the glasses away from his eye in order to gain magnifying effect or to make the image on the retina, as this is said to be increase the effectivity. The reverse happens with myopia, as both this myopic patient has larger eye, they have larger refractive system, the light rays converge to make a focus in front of the retina. So what happens when we are putting a minus lens, the light rays diverge, making it more directing toward the eye or more backward. The focus is shifted more backward until it reaches the retina. So in order to make the focus on the retina, we can either increase the power of the minus lens, or we can move the minus lens toward the eye, because if we move the minus lens away from the eye, what happens that the focus will move forward again, so it will be away from the retina, causing decrease the effectivity. But what happens if we move the minus lens toward the eye? Again, the light rays will be focused on the retina, causing increase in the effectivity. That's why the myopic patient tended to push his glasses toward his eyes in order to gain magnifying effect. And the practical example for this is the correction of aphakia. So aphakic patient, when they wear glasses, it will be power of 11.7 diopters. But if we shift to contact lens and we are moving more toward the eye, the lens power or the effective power of the lens will decrease, so that we should increase the power of the contact lens to be 13.8 diopters when replacing the spectacle to contact lenses. So I hope that this is clear now. Let's now move to the next question, and here we have regarding the optics of the thick lens, which one of the following is most likely to be true? And the anterior and posterior vertex focal length differ by half thickness of the lens, or the equivalent power is the anterior vertex power plus the posterior vertex power. Power is calculated from the two surfaces power, and the correction for thickness or the principal points lies on the surface of the lens. C is the right answer. So let's analyze the question. The anterior and posterior vertex focal length are not different by the half of the thickness of the lens. This is not true, and this is not mentioned in the equation. The equivalent power of the anterior vertex power plus the posterior vertex power, no. This is the power of the thin lens. It will be equal to the anterior surface power and posterior surface power. But this algebraic summation of the anterior and posterior surface doesn't work for the thick lenses, because we have another factor, which is the distance between the anterior and posterior vertex lens, and this is the thickness of the lens. So the power of is calculated from the two surface powers and correction for the thickness of the lens. The principal point lies on the surface of the lens. This is not true, or it can be on the surface, but this is not the only case. It can be outside as well. So let's see, this is the example of thick lens. When we have multiple lenses separated from each other, then the total power will not be the algebraic summation. But there is another formula called the Goldstran's equation for thick lens power, in which the power of the lens would be equal to the power of the anterior surface plus the power of posterior surface minus power of the anterior surface multiplied by the power of posterior surface multiplied by the distance between the two surfaces of the lens, which is the thickness of the lens, divided by the refractive index of the lens. Here is, you can see what is the anterior vertex focal length and posterior vertex focal length for concave minus and concave and convex minus lens. We said that the optical center can be coincides with the geometrical center for biconvex and biconcave. But in case of plano-concave or plano-convex, then the principal point doesn't lies on the center or doesn't lies on the plane surface. They lie at the curved surface, the more curved surface. But if we have a meniscus lens, then either positive or meniscus, then the optical center doesn't coincide with the geometrical center, but they are lies outside the more curved surface. So the principal point doesn't always lie on the surface of the lens. Anterior vertex focal length is the distance between the anterior surface of the lens and the f1 of the convex lens and f2 of the concave lens, while the posterior vertex focal length, it is the distance between the posterior surface of the lens and f1 of the convex lens and f2 of the concave lens. Here you can see the anterior vertex focal length is the distance between f1 and the anterior lens surface, while the posterior vertex focal length is the distance between the posterior surface and f2. On the other hand, the concave lens, the anterior vertex focal length is the distance between the f2 and the anterior surface, while the posterior vertex focal length is the distance between the f1 and the posterior surface. Regarding the power of the unknown spectacle of the lens when viewing through a cross, when the lens is moved, which is true, both lines of the cross are displaced if the prism is present, or it can be used to determine the power but not the axis. The cross appears to move in the opposite direction if it's a concave lens, or the power determined is likely to be inaccurate if the power is over 5 diopters. The correct answer is that the power determined is likely to be inaccurate if the power is over 5 diopters, so I will give you the explanations of the other options. Both lines of the cross are displaced if a prism is present. No, it is only a single line that will be displaced. It can be used to determine the power but not the axis of the cylinder. I used to think that this is right, but when I thought about it, it is the wrong answer, as the cylinder can still be used to know the axis if we place the cylinder over the lines and no distortion happens. This means that the cross is aligned with the axis of the astigmatism. The cross appears to move in the opposite direction if it's concave lens. No, it will move on the same direction if it's concave lens, or opposite direction if it's a convex lens. And the power determined is likely to be inaccurate if the power is over 5. So here we have a concave lens, and we can see that there is, if we move the lens in one direction, there will be displacement of the lens in the same direction, or the displacement of the cross on the same direction, and it will be minified or becoming more thin. While in the astigmatism, when we place the lens on the cross, there will be scissoring movement on rotation due to unequal refraction of different meridian. The astigmatic lenses cause distortion of the cross, but unless their axes coincide with the cross lines. And this is how can we know the axis? By making the cross coincide with the axis of the astigmatic lens. Once we put the astigmatic lens and we find no distortion, then this is the axis of the astigmatic lenses. So with further rotation of the lens, this will cause scissoring movement, and the cross lines are progressively displaced like this. We rotate, then the lines will be displaced. The prism lenses has no optical center, so it will displace one line of the cross regardless of the position of the cross. It will cause displacement, or the direction of displacement is always constant. It is toward the apex. As you can see here, once we put the prism lens, it will cause displacement toward the apex. Next question about the Knapp's rule. So according to the NAPS rule, it concerns the correction of coma in patients with astigmatism, or it's a way of measuring the critical angle, which induces total internal reflection, or anisometropia due to different axial lenses is better corrected with a spectacle than contact lenses, or it is a quantification method to link between the accommodation and the accommodative convergence. So see, here is the right answer. The NAPS rule is a rule made by a scientist called Knapp. He made a mathematical calculation in order to know if regarding the anisometropia and the anisoconia. If the patient has anisoconia, what will be the best method to correct it? How to decrease the anisocoria to the minimum? According to Naps, he has a theory that if we use a spectacle for axial anisoconia, this will result in the least anisoconia. And if we use contact lenses for refractive anisoconia, this will result in the least anisoconia. So he made some mathematical calculation to calculate the relative spectacle magnification in case of axial anisometropia and in case of refractive anisometropia, and he found out that in axial anisometropia it will be better to correct the patient with the spectacles, while in case of refractive anisometropia it will be better to correct the patient with contact lens. And the reason behind his theory that he said that if the ametropia is axial and we are correcting the lens placed before the eye, then the second principal point coincide with the anterior focal point of an axially ametropic eye, then the size of the retinal image will not change. It will be the same as ametropic eye. But if there is a patient has refractive myopia or refractive hypermetropia, so in this case, the undercorrected or uncorrected image size will be the same like the ametropic image size. But the problem is with correction. If we put spectacles, then the spectacle will cause either magnification for plus lenses or minification of the image with minus lenses. But the contact lens has less pronounced effect. It will cause less magnification and less magnification. That's why it is better to correct these refractive myopia or hypermetropia with contact lenses, which will cause the minimal anisoconia or to make the image size almost unchanged. Okay, let's move now to the next question regarding the optical power of the normal human eye. Which one of the following statements is true? A 25-year-old can increase the power by 20 diopters, or most of the refractive power is provided by the cornea aqueous interface, or the cornea has the highest refractive index of all ocular structures, or the radius of curvature of posterior surface of the cornea is smaller than the anterior surface. The final answer is the correct answer. So a 25-year-old can increase the power by around 8 to 10 diopters, and most of the refractive power is provided by the corneal air interface due to different refractive indices of the both media in front and behind. The cornea doesn't have the highest refractive index, but the lens has higher refractive index, and the radius of curvature of posterior corneal surface is smaller than the anterior surface. This is the correct answer. The relatively greater power of the cornea is due to the greater difference in the refractive index between the air in front and the aqueous behind. This is what will cause the major refraction occur at the cornea. But the cornea doesn't have the highest refractive index, as the lens has a higher refractive index or has the highest refractive index than the cornea. And the power of the cornea, we said it is attributed to the difference between the refractive indices of the media in front and the media behind. So the more the difference between N2 and N1, then the more power of the cornea. So the power will be equal the refractive index of the second medium minus the refractive index of the first medium divided by the radius of curvature. And according to the measurements of the cornea, we mentioned before that the radius of curvature of the posterior corneal surface is less than that of the anterior corneal surface. Let's move now to the next question regarding the schematic eye. Which one of the following is true? All distances are measured from posterior corneal surface, or it has a refractive power of approximately 58.6 diopters, or it has a single nodal point in the posterior pole, or the first focal point is posterior to the cornea. What will be the right answer? Yes, it is B. It has a refractive power of approximately 58.6 diopter, which make it different from the Goldstrand eye. So all distance are measured from anterior corneal surface, and it has two nodal points that are straddling the posterior lens, and the first focal point is in front of the cornea. So let's see here, as we mentioned, that the schematic eye cardinal points, they are measured from the anterior corneal surface, and we have six cardinal points, two principal foci or two principal points, two nodal points, two focal points. The two nodal points are straddling the posterior surface of the lens, as you can see here, and the anterior focal point is in front of the cornea. The reduced eye has a power of 60 diopter, like this is the Dunder's reduced eye, but the Goldstrand schematic eye has a power of 58.6 diopter. The next question is about the catoptric images, again Purkinje-Sanson images. For it is easier to see in a pseudophakic eye, or it is located in the anterior vitreous, or it is the only virtual catoptric image, or it moves when the eye accommodates. So 4 is the right answer, or D is the right answer. It moves when the eye accommodates. This is the correct answer. It is difficult to see in the pseudophakic eye, as the difference between image 3 and image 4 is the thickness of the lens, and the phakic eye has more thickness, so they are more displaced. But in pseudophakic eyes, they are the IOL will have much more thinner, much be more thin than the human crystalline lens. The image 4 is located on the posterior surface of the lens, and it is a real image. It's the only real catoptric image, and it moves when the eye accommodates. This is the correct answer. So again, we mentioned that we have four catoptric images. The image 4 is formed by the concave surface of the lens, and it will be the only real real inverted image. And the clinical application that image 3 and image 4 are used to study changes in the lens during accommodation, as during accommodation the lens bulge, the most of the bulge is in the anterior surface with the minimal bulge of the posterior surface. So both image 3 and image 4 will change their locations. Let's move now to the next question regarding the activated lasers. Which one is true? A partially transparent mirror at one end will produce Q-switched laser, or lasers may produce light of more than wavelength, or length of the tube is proportional to the wavelength of the light emitted, or there are more outer shell electrons in unexcited state than excited state. The second answer is correct. So lasers may produce lights of more than wavelength. Like for example, it can produce femtosecond laser, which is infrared laser, or excimer laser, which is ultraviolet laser. So it can be of more than one single wavelength. The partially transparent mirror at one end of the tube will produce a continuous wave laser, not Q-switched laser. As in Q-switched laser, there is shutter which is placed in front of one mirror to allow passage of shots of laser to maximize energy and minimize the loss. The length of the tube is directly proportional to the wavelength of the light emitted, which is important for resonance and for making the summation of the wavelengths. There are more outer shell electrons in excited than unexcited state, and this is what's called population inversion, and it is important for laser mechanism. So let's see this video, which can show you the mechanism of laser. First, we use a medium. This medium can be a solid or gas or even liquid that has atoms. These atoms has then it will be present in the tube and has a mirror at one side and a partial transparent mirror at the other side in case of the continuous wave, and then there will be a source of light or what's called the pumping. This energy input or the pumping will produce a light. This will light causes stimulation of the atoms present at this medium. And this atom has a nucleus and has electrons. These electrons are in ground state. When the electrons are excited by the pumping, then they will move from the ground state to the higher energy state. And this is now an excited atom. This excited atom is unstable. So in order to reach again to the ground state, it will emit energy. This energy is in the form of coherent light that has specific wavelength. If we leave this, then all these millions of atoms will produce the same light of the same wavelength. And now this is the rule of the tube to have the of length of multiples, to have the length of the tube to be multiples or multiplications of the wavelength of this emitted light. In order for this light to be multiplied going back between these two mirrors and causing multiplication and causing that the laser will be becoming more coherent and more intense, so that it can come from the partial transparent mirror as a continuous wave laser. So here are again the laser elements. It consists of an active medium like a gas or solid or liquid, and which makes the light monochromatic, and a source of light or what's called pumping energy input that will cause stimulation of the atoms present in this medium. This will cause what's called population inversion, in which the more electrons are becoming from unexcited state to the excited state, or traveling from the ground to higher level. These electrons are unstable after the pumping and the population inversion. They become unstable, so they release their energy in the form of coherent light, and then it will bounce between the two mirrors within the active medium, which is called the resonance, until they are emerged from the partial transparent mirror as a continuous laser. Here is the same again. So we can see here that the electrons are present at the higher orbit are in excited state, while those who are at the ground are unexcited state. For the electron to become unexcited, it will release the energy to reach the ground state. Okay, let's move now to the next question, asking about the epidemiology of the uncorrected refractive error, which is most likely to be true. It will be the commonest cause of visual impairment worldwide, or the development of myopia can be reduced by indoor sports. The most common refractive error is astigmatism over one diopter, or the prevalence of myopia but not high myopia is increasing worldwide. So the correct answer, it is the commonest cause of visual impairment worldwide. The development of myopia can be reduced by the outdoor activities, like sports activities, but indoor activities use any sport or any activities indoor will make someone look at a closer distance, leading to increasing the accommodation, increasing the myopia. So outdoor will be the best. The most common refractive error worldwide is myopia, and the prevalence of myopia is high for both myopia and high myopia. So these questions you should or use to appear at the public health section of the clinical ICO. And so let me tell you for the cause of visual impairment. The commonest cause of visual impairment are uncorrected refractive error, followed by the cataract. But for causes of blindness worldwide, the most common cause of blindness will be the cataract. The prevalence of myopia is about 33%, making it worldwide, making it the most common ocular problem worldwide, and also the most common refractive error. It is being more in the eastern part of the world, more in China and Singapore, while the prevalence of astigmatism is like about 20%, and it is different according to as it is highest in the first months of life, as the curvature of the cornea is very steep, while again the Asian show relatively high prevalence of astigmatism. Final question regarding the fluorescence used in ophthalmology, which is true. Fluorescence stops as soon as the stimulating light stops, or indocyanine green absorbs the light at 535 nanometer in infrared range, or it's the ability to emit light of shorter wavelength than stimulating light, or it occurs when a substance stimulated by green light emits blue light. So the right answer is the fluorescence stops as the stimulating light stops. So when we are presenting a stimulating light, always remember the famous example of the applanation tonometry. When we are measuring the intraocular pressure, or when we are checking the ulcer, you are stimulating by the blue light, and the fluorescein strips are orange, and we got a green light of the ulcer. So we are stimulating by the light and we get green. And once we stop the stimulation by the blue light, we stop the green color stops. The indocyanine green absorbs the light of 805 nanometer in the infrared range and emits 835 nanometer. So this is the emitted light, not the absorbed light. It is the ability to emit light of longer wavelength than stimulated light, and it occurs when substances are stimulated by the blue light emits green light. So I made this table to make it easier for you to remember. Generally speaking, the fluorescence is when the stimulus or the light is absorbed is of shorter wavelength, like the blue. This fluorescent material will emit longer wavelength, like green, and this will stop as long as the stimulus will be stopped. So what is the spectrum of the fluorescein sodium? What will absorb and what will emit, and what will be spectrum of IgG, and what will absorb and what will emit? The sodium fluorescein will absorb the blue light at the range of 465 to 490 nanometer and emit green of wavelength of 520 to 530. On the other hand, the IgG will absorb 805 and emit 835. So fluorescence, as we mentioned before, it is the property of molecule that will making it emit light of longer wavelength when it is like green, when it is stimulated by shorter wavelength like the blue. For example, the fluorescein dye or fluorescein sodium will emit yellow-green light when it is excited by the blue light, as you can see here. This solution has sodium fluorescein and it is stimulated by the blue light, so you can see it is emitting green light. And if we stop this blue light, this green light will stop. Examples are the fluorescein strips and the fluorescein solution used for injection in the fluorescein angiography. So the fluorescein strips can be used for measuring the intraocular pressure, staining of the corneal ulcers, while the fluorescein angiography, the fluorescein is used for intravenous injection in order to delineate the choroidal and retinal vasculature. It depends on this mechanism, so there will be a white flash. It will the fundus camera has a camera flash that will produce white light. It will pass through a blue excitation filter that will cause the light to be blue. This blue light will hit the retina, so it can be absorbed by the fluorescein molecules, leading to reflection of green light, and the areas that will not absorb the fluorescein molecule will not be stained or will not reflect the green light, so it will be only blue. And the the here the green, the both reflected green and blue light will pass through a green barrier filter, which will allow only passage of the green light, leading to it will hit the camera and it will hit the film, showing the pattern of fluorescence from this fundus image. So it will show the choroidal flush, can show the blood vessels within the retinal blood vessels, and can show patterns of abnormal fluorescein like leakage, as you can see here. On the other hand, the other dye, it is ICG. This is another fluorescent substance, but it absorbs and emits light of infrared spectrum. So it will absorb with 805 and emits longer wavelength light of 835. The main advantage of ICG that the RP does not absorb these wavelengths of infrared. So it is important. So it is useful to observe the fluorescence of the choroidal circulation, so that it will this ICG is administered intravenously, as only 4% of this 805 nanometer radiation absorbed by the ICG is emitted at 835 nanometer compared with the total fluorescence of fluorescein. So this is the end of today's lecture. We had just also, we mentioned in the live lecture that there will be winners for the live contest. So the third winner will have $25 coupon for discount of any next courses. The second winner had won $50 coupon for the for future course purchase, and the first winner had won $75 coupon for purchase of any future course. Congratulations for the winners, and good luck for others, or for other candidates for the next live sessions. Thank you for attendance. Thank you for the candidates who attended the live sessions, and apologies for the technical error that happened and made the live session not recorded, but it was the same information and same question that we discussed. And I hope that you find this recorded lecture useful for you, and it helps you to enlighten your path as you study the optics. Thank you all.